Good afternoon. Glad to see you guys here. It's my honor to introduce our speaker today. Dr. Lorin Matthews graduated from Baylor as an undergrad, summa cum laude, and then 4 years later picked up a PhD here as well. Right out of Baylor, she went off to work with Raytheon, which is now L3, working on the NASA Sofia project as a vibroacoustic engineer. And somebody in this room, I won't say who, kept talking to her saying, you're really going to get bored. You ought to take a big pay cut and come over and work with me. And she finally agreed with me, so she did. Along the way, she's gotten all sorts of funding, published lots of papers, and one of the best parts of the funding was an NSF Career Award, which the title of her career award was Charging and Coagulation of Dust Grains in Astrophysical and Laboratory Environments. So you can see that she's been doing this for a long time and doing it very well. So please join me in welcoming Dr. Matthews.
Thank you. So I'm going to be talking again about charging of grains in astrophysical environments. And a lot of this work was done in collaboration with my graduate students, undergraduate students, postdocs, research faculty. So I have a lot of names here on the slide that have contributed to this. So first, just to talk about why are we worried about dust in space and where do we find dust? So actually dust is everywhere. We can't get rid of it. It's not just under your bed. It is everywhere in space. So this is one of the newest pictures from the James Webb Space Telescope. This is called the Cosmic Cliffs. This is a section of the Carina Nebula. And what's kind of interesting is like those knots up at the top, those are 7 light years across. So this is really huge, and this is gas and dust in space. And those little knots are where stars are starting to form. And so here's another picture that you've seen a lot. It's a Hubble Space Telescope picture. These are called this is the Eagle's Nest Nebula. And once again, you can see those little knots. What's happening is the really high energy gamma rays from the other stars behind it are actually evaporating the dust and blowing away the gas. And so it's only in the regions where the cloud has started to collapse and you have really high energy, high density, that you leave the material behind. And it's those high density regions where you're forming stars. So sometimes they call this the Eagle's Nest Nebula because then you have all the little baby stars being born in the nest. So what does that look like? So when you actually have a star that is born, it's from this collapsing cloud, and as the cloud collapses, because of conservation of angular momentum, it spins up faster and faster, and so this spinning dust cloud tends to kind of flatten out, kind of like pizza dough, if you are so apt as to be able to throw pizza dough in the air and actually have it spin. Has never worked for me. I've tried. But anyway, so you get this flat disk, and the stars also do something special where when they start fusion, they actually start blowing off solar wind, and they blow off preferentially at the poles, so they blow off the top and the bottom. So you're left with this very flat disk. And so these are called proplids, or protoplanetary disks, which were hypothesized to exist, and they finally discovered them in 1995 when the Hubble Space Telescope was able to take these pictures. And then with some other pictures, you can see the here's some edge-on disk, and you can see they're actually very thin. So these disks are actually where you start to form the planets, and so that's why all the planets are in the ecliptic plane rotating about the star. So here's some other pictures, though. It's not just star birth, but also star death. We have a lot of dust and gas. So this is a picture, again, taken by the James Webb Space Telescope. And it's 2 different wavelengths of infrared light. And you can see different dust structures. So in this wavelength, you can actually tell that star that's at the very center is not just one star, it's actually 2 stars. And it's actually the dimmer star, the fainter star, is the one that's dying and blowing stuff off. And so they said, we're kind of looking at this edge-on. If you weren't edge-on, it would be like 2 inverted bowls where the dust is being blown off around it. Okay, and this is another picture that I really like. This is from the Sofia Telescope, which is also an infrared observatory. And this one, they were looking at the polarization of light. So as the light is passing through the dust, it actually gets polarized when it's re-emitted by the dust, because the dust grains, if they're charged, they tend to align with magnetic field lines and emit polarized dust. And so they're actually able to map the polarization directions on this background image of stars, and so that you can actually map out the magnetic field lines in a stellar cluster or in our galaxy. And it's the dust in the space that allows us to do that. If we get a little bit closer to home, this is one of Saturn's rings, Saturn's F ring, and you can see it's visible outside the main rings. It was discovered by the Pioneer probes in the 70s because it's very faint, because it consists of dust. But you can see that it's got lots of interesting wiggly features. It just doesn't stay nice and smooth, and this is because, possibly because the dust in there is charged and interacting with the magnetic fields. Here you can see that as a moon passes by, it actually pulls off streamers of material. And Jupiter has a dusty ring, and Uranus also has dusty rings, so we see dust rings everywhere. A little bit closer to home, again, we have the moon. So this is a picture of the sun is behind the moon, actually, in this picture, but we actually see this lunar horizon glow. The moon doesn't have an atmosphere, so it's not like the light is being scattered in the atmosphere of the moon. Instead, what they think is that dust is lofted above the surface of the moon, and so the light is actually being scattered by the dust that has been lofted. So then a good question is, what is kicking up dust on the moon? It's not giant space bunnies. I'll just give you a hint. But one of the things that happens is that the dust gets charged by the UV light just from the sun, and there's actually a potential difference between the day side and the night side of the moon. And so because of this potential difference, they're still trying to figure out, is this potential difference enough actually to lift dust particles up off the surface, and can you lift them this high, and how do they stay lofted long enough? And this is a picture of one of the astronauts who came back, returned from a lunar walk, and you can see that his pristine white spacesuit is completely covered with black dust. So it's a real problem for lunar exploration because the dust is kind of nasty. They don't have any weathering on the moon, and so the dust has very sharp edges. A lot of it is from volcanic glass, and so you can imagine that it's very sticky dust, and I mean sticky as in it sticks to you, and sticky as in it's pointy. So both of those are bad if you get them on your spacesuit because you're trying to rub it off and it's just abrading your spacesuit because it's very sharp. And if you get that back into the lunar capsule, then you take off your spacesuit and now you finally do knock some dust off. It's floating around. It doesn't settle because it's charged. And then the astronauts are breathing it in. And you can imagine that breathing in sharp, sticky dust is not good for your lungs. So it breaks seals, it causes the equipment to abrade, dust is just really bad. So this is another thing they're going to have to deal with on the moon. So that's kind of a little bit about where dust is. And so I'm going to tell you a little bit about how we model the dust and how it moves around, because the dust is not just dust by itself, it's almost always immersed in a plasma environment. So plasma just being ionized gas, you have electrons and ions, and what we call plasma is not necessarily the inside of the light bulbs, but out in space, interstellar space, you have one hydrogen atom here, another hydrogen atom way over here. That's the plasma when they're ionized. So it can be a very tenuous plasma, but you've got big distances, you also have long times, so things can charge up and you can see actual effects. So we're going to talk about how it becomes charged, and then what do we do when, as physicists, we're confronted with the fact that everything is not a sphere. So how do you charge irregular grains, and then how do these grains move around? Okay, so first of all, plasma. You know what a plasma is. You have a gas, you have the nuclei, you have the electrons, and if you apply enough energy, you can actually give the electrons enough energy that they can escape. And so you'll have electrons, and then you'll have ions that are left. So if we put dust in it, it becomes complex. And because the electrons are more mobile, the electrons run into the dust more often, more frequently, and the dust is going to become negatively charged. And then the negatively charged dust will repel the electrons, and it will attract the ions. And so there's this characteristic distance around the dust that we call the Debye length, and it's given lambda sub d is the character we use for that. And the importance of this distance is that, we take our normal Coulomb potential, which is just kq over r, and because you're attracting more positive charges around it, these positive charges act to screen the negative charge on the dust. And so the Coulomb potential is a shielded Coulomb potential, and the Debye length is the point at which the normal potential is reduced by a factor of 1 over e. So we have the regular Coulomb potential, and then you have this extra exponential term. So sometimes you'll hear it called a Euclid potential, sometimes it'll be a shielded Coulomb potential. They come up with a whole bunch of different names to call it, but it's all the same thing. Okay, so that's what a dusty plasma is, and so now let's talk about how you actually get the charge on the dust from the electrons and ions. And actually, so that's the primary way that a dust grain becomes charged, is you actually have what we call the primary currents, which is electrons come in and hit the dust and stick, or ions run into the dust grain and stick. But then you can have other things. One, if you have really hot electrons, they're very energetic, the electrons can come in and they'll actually tunnel into the material, and they're giving up energy all along that path, and that energy can then be picked up by other electrons, which then can leave the surface. And so that's called secondary electron emission. So you have the primary electron come in, and then it knocks off the secondary electrons, and so that can lead to a positive grain charge. And then another effect is that you can have photoelectric charging. So if you have high energy photons, they can come in, hit the surface, transfer their energy to electrons, the electrons get knocked off, and things will charge up positively. So what we look at then is we have all of these currents. You can think of these electrons and ions running into the grain, or the electrons being knocked off, as currents. Current, of course, is just a change in the charge with time. So if we add up all of the currents to the grain, that is going to be equal to the net change in the charge with respect to time. Now the currents are going to depend on the surface potential of the grain, because if the grain is already charged, if it already has a negative charge on it, it's going to be hard for it to lose electrons by, say, secondary emission or photoemission. It will attract ions to it. It would repel other electrons. And so we have to worry about that. Now, we can reach an equilibrium condition when the charge is no longer changing in time. So when dq dt is equal to 0, the sum of the currents is equal to 0, we can come up with an equilibrium charge, or an equilibrium surface potential. And we also have that the charge then, of course, is related to the potential just through the capacitance. So we can use the capacitance for a spherical grain, and once we know this equilibrium potential, we can actually figure out how much charge is living on the grain. So how do we actually calculate the charges? So let's just look at the primary currents, and we're going to treat the electrons and ions coming in and hitting the grain surface as a flux to the surface. And you know how to calculate flux. Flux is just the velocity dotted with the area. So we have this v cosine theta. So, and this is going to have units of volume with respect to time, because the velocity is in meters per second, the area is in meters squared, so this gives us meters cubed per second. Now, that's just the flux of particles, and we want to know about is the flux of charge, which is what's going to give us our current. So we take N, which is the number density of the electrons or ions, so the number per volume, and then we multiply by the charge Q on the electron or ions. And so now this has units of charge over time, which is what the units of current is. But then what we have to do is not all of the electrons and ions are coming in at the same angle. So we actually have to integrate over all possible velocities, all possible speeds, and all possible directions. So this is what we would actually do. The total current then would be to take this, and what we need to know is we use the distribution function, and usually we can assume that the electrons and ions are thermalized so that they're going to have a Maxwell-Boltzmann distribution. So we know how many particles will have each speed and integrate over all of the velocities in all the directions. And so we can get the total current. Okay, but what is that target area? Because it matters how big your target is. The bigger the target, the more electrons and ions are going to hit it, so the bigger current you would have to it. So to calculate that current area, here the current area has turned into this sigma sub alpha. And we also then, when we integrate, we have set a lower bound on the speeds. And why are we doing that? And that's because we can either have electrons or ions coming in and hitting the target. And then they're going to have a certain density, and they're going to have a certain charge. And they're going to have a certain minimum velocity to reach the surface. And this minimum velocity is related to something that we call Oml theory, which is orbit motion limited. And I'll show you why it's orbit motion limited in about 3 slides. But our important thing is we need this collision cross-section. That also comes out of the orbit motion limited theory. And then, of course, our d cubed v is a integral over all of the possible speeds, and it's over the full solid angle d omega. So we have to determine all of those. So here's Oml theory. So Oml theory is based on, of course, conservation laws. We have conservation of energy and conservation of angular momentum. So first, let's talk about conservation of energy. So what happens then is this is how we figure out the minimum velocity that you have to reach the target. So we say that the potential, the kinetic energy of the particle very far away, where the potential energy is 0, has to be equal to the potential energy right at the surface, assuming that it just came to rest at the surface. So you set kinetic energy 1/2 mv squared equal to the potential energy QE, and we can solve for the velocity. And we can see that if the charge of our particle, the electron or ion, multiplied by the potential on the dust grain is negative, so, all right, negative potential, a negative dust grain, and a positive ion, positive times negative is negative, is going to be less than 0. The minimum energy, minimum velocity is 0 because it's being attracted. It could just be sitting out here and the force will gradually pull it in. But if Q phi is greater than 0, we have an electron and a negatively charged grain, then the electrons are going to be repelled. And so they have to have a certain minimum velocity to overcome this Coulomb force and actually hit the target. So we have this minimum velocity. And so, whoops. Well, there we go. I hit my buttons too fast, but whatever. Oh, now I'm going backwards. That's a very slow animation. Anyway, the electron missed the target. That was the important thing to know. All right, the second part of Oml theory is that we have conservation of angular momentum. And so basically what this does is it effectively changes your target area. So if you have a negatively charged grain and you have a positive ion, well then the ion is going to orbit and be attracted to it. And, whoops, oh, I know, I'm hitting the wrong button. Effectively, that just makes the target bigger because you have the impact parameter. And then if you have a negative electron, the electron is going to be repelled, and so that essentially makes your target smaller. And so when you work that out, you can just see that your target area, which would normally be pi a squared, where a is the radius of the grain, it is increased if q phi is negative. That's a positive ion and a negative dust grain, and it shrinks if q phi is positive. That's a negative dust grain and a negative potential. Okay, and then orbit motion limited. So any particle that orbits the dust grain is assumed to be part of the charge on the dust grain. And so that's why it's orbit motion limited. So we're not having to sit here and worry about the ions that are just circling around and around. Okay, so that's Oml theory. All right, so we put it all together. We actually do the integrals. I invite you to actually do these integrals and see if you can come up with this result. That the electron current, notice that the electron current falls off exponentially with E phi, while the ion current grows linearly with E phi. And this is assuming that you have a negative grain. And most things do charge negatively because the electrons are zipping around and it's going to collect electrons first. And in the steady state, we can just simply set the electron current equal to the ion current. So we set those two equations equal, and we do a little bit of algebra to clean it up. And then let's see what kind of surface potentials we actually get. So a classic case is to assume, let's say that we're out in space and you have hydrogen. And so every hydrogen atom gives you one proton and one electron. So the number of electrons is equal to the number of ions. And because it's out in space and it's been hanging out there for a long time, it's had time to thermalize so that the temperature of the electrons is equal to the temperature of the ions. Then we can clean up our expression a little bit more. And it's a transcendental equation, but that's no problem. We can just graph it. And so we have the linear part and the exponential part, and then where they cross, you can see that that's the potential where we're going to have a charge balance, or the black line is just the two halves added together. And so that black line crosses right at about negative 2.5. So the potential is negative 2.5 multiplied by the temperature of the electrons and ions, kT per E. So this is kind of the classic result, and you get this negative dust grain. And it will be different depending on what gas you're in, because remember we assumed a hydrogen plasma, so we use the mass for hydrogen. And a lot of times the temperature of the electrons and the ions are not equal, so you have to take into that account. Okay, so that's how we charge a spherical grain. We understand that very well. We've done experiments. The theory actually works pretty well. What happens when you have an irregular grain? Well, what we can do is we can take the ideas of Oml theory and we can modify it, because remember for the Oml theory we had to integrate over all possible velocity directions. But when you're sitting on an aggregate surface, for electrons or ions to come in and hit this point, they can only come in from a very small angle. Whereas if you're over here, electrons and ions can come in from this full half direction. So we can change up our integral and look at these directions, and we're going to replace this numerically with something we call the line of sight factor. And the idea is that we only integrate over the lines of sight which are open. So what we can do is we can take our aggregate, we can put points all over it, and for every single point we can look in all of these directions. And you look, is that an open line of sight, or is that line of sight blocked by either the monomer it's sitting on or another monomer in the aggregate? And so then instead of doing that nice neat integral, we have to do a sum over the cosine theta, and then the solid angle that's associated with each of your directions that you looked in. And we look in some insanely large number of directions, like 1,000 or something, to get it really accurate. You can play with the accuracy there. But if you are on an isolated sphere and nothing else is blocking it, the line of sight factor is equal to pi. So the line of sight factor varies between 0 and pi. So when we do that, now we can calculate the charging currents to all of the points on the surface and see how they charge up with time. And you'll notice that most of the charge collects on the extremities, which is kind of what you would expect it to do. And you will see that you get more charge on the outside edges. And also, even though, say, the biggest aggregate would have the most charge charge on it, the charge densities are going to be highest on these little bitty grains that are on the outside. Okay, so now we know how the grains charge up, and we're interested in the grain dynamics. What difference does it make when we have the charge rearranged like this? So the first thing is just looking at, let's say that you're in a protoplanetary disk and you would like to start building a planet. How do you get the dust grains to stick together? And so you're going to start with these spherical monomers that have condensed out of the gas, and they run into each other and stick. But when they stick, they don't create a new sphere. They start adding up, and you start building these irregular structures. So one of the things you have to worry about is, as they're coming in, you have to worry about the electrostatic interactions, and then because you have this arrangement of charge, you actually get torques that are acting on the aggregates, and so they're going to be rotating as they're sticking. So we get very spherical potential contours, which is what that shows. So we can treat this as a multipole moment when you're far away. A dipole moment is good enough. Quadrupole moment's really good. But then when you get in close, you might actually run over one of those poles, and then your simulation will go haywire. So when it gets in close, you can treat each individual sphere as a point charge and get a very accurate kind of multipole and track the incoming dynamics of the particles that way. Okay, and so what happens then is that depending on the plasma environment, what the temperature is and how much plasma there is, you can get very different dust bunnies. So this aggregate here was grown in a plasma environment where there's just not a whole lot of charge around. And so this has 2015 spherical monomers in it, but most of them you can't see because they're the very tiniest monomers. And in space, this is the way dust is arranged. It has what we call a power law dependence. And so you have a whole lot of the really small dust and just a little bit of the bigger dust. So there's a lot more small dust, and that's what you see in this one. In the aggregate that's on your right, it also has about 2,000 monomers, but it's a lot bigger. And you notice that the monomers that are in it are much bigger. And that's because all the little monomers that have this small charge, they can't overcome that Coulomb repulsion barrier, and so they get repelled. And it's only the big monomers that have enough inertia to come in and collide and stick. Even though they have bigger charges themselves, they just also have the inertia bit. What? R sigma, I will explain on the next slide. Basically, R sigma is an equivalent radius, and there's a way that you calculate it. So R sigma would be related to the radius of a sphere that has an equivalent projected surface area. So basically, you would take your aggregate, you project it on a screen, you calculate the area on the screen, you set that area equal to a circle, and calculate the radius. And then you look in a different direction, and you look in a different direction, and you average that over a whole bunch of directions. And so R sigma is always something a little bit smaller than the actual size of the aggregate. Uh-huh. Oh, yeah, the size of the aggregate? No, the size of the aggregate is independent of lambda. So lambda is a screening length in the plasma. And the size that you can grow your aggregates is fairly independent of lambda. Okay, so another thing we have to worry about is the dynamics and their relative time scale. So if you're in the lab, the charging is really, really fast. And so as two aggregates are approaching each other, they're going to be blocking those lines of sight. And so the charge on the particles is going to be changing as the particles are colliding with each other. So the dust itself will be moving on like a millisecond time scale, whereas the charging occurs on a microsecond time scale, because that's how fast the ions can move. So we would have to recalculate charging as the dust is moving around in the laboratory. It's a little bit different if you're out in space, because out in space there's not that much plasma. If you're in a very tenuous environment, the collision time scale is going to be fast compared to the charging time scale. And in that case, the charging doesn't change as they collide, and you can see that you get very different outcomes, just depending on the timescales of what's going on. And another thing we have to worry about is stochastic fluctuations of the charge. So a stochastic fluctuation is intrinsic noise that you get because the electrons and the ions are coming and hitting at random time intervals. So instead of just having a nice smooth average charge, you're actually always fluctuating about the average charge. And so let's say that you have a small grain and the average charge is about 67 electrons. The charge can fluctuate everywhere between 50 to 85 electrons. And so you want to know, and as the charge fluctuates, it can change the potentials a lot. So even though you have a spherical grain, you're going to get these asymmetric potentials that can change. So this, if you're on very small grains, less than a micron in size, and especially out in space where the plasma is very tenuous, your average grain charge may only be 2, 3, 4 electrons. And so then if you fluctuate, you can have very difference. And actually, if you have really small grains, the grain charge can fluctuate between positive and negative, and that will change the dynamics a lot. And so, you know, this is what a neutral grain looks like. And if we look at the time averaged charge, you know, over a long time, we would get all the charge over here on the extremities. And it actually makes a difference whether you just treat the average, if you take all of the charges, say, on this sphere, and you add them up and calculate the charge, you can get a fluctuation that's just on each sphere. Or you can actually let it fluctuate on each individual point and treat that with the dynamics. And so there was one paper that we did where we actually tested this to see what made a difference. So if you grew aggregates in a neutral environment, you get very compact aggregates. And here the outer sphere, the outer green sphere, shows the distance from the center of mass to the furthest extreme point on the aggregate. And the inner sphere has the radius of that R sigma, that effective cross section. If we use the time average, so now if we have charge dust, but you just use that average charge that gets over the body, you can see that you get slightly fluffier dust, you get fluffier dust bunnies. But if you use the discrete stochastic charges, so you're actually counting the number of electrons and ions and how it's actually fluctuating in time as you're aggregating, it makes a big difference and you actually get even fluffier dust bunnies. So you want to be careful in your numerical modeling that you're not obscuring some of the physics going on so that you know what the time scales involved. So, and this is what they look like when we grow them in the lab. So these are aggregates that are grown in our lab. These are melamine formaldehyde coated with gold. And notice that they're very irregular, and they all like to rotate. So they're kind of hanging in place, but they rotate. And this is in, it's a very low pressure, you know, maybe 25 pascals, something about like that. So very low pressure system. These are aggregates that are grown in situ from water ice using a very cold chamber. And so you can see that you get very different aggregates when they're grown in helium versus grown in a neon plasma where the ions are more massive. So in the helium plasma, they get really long, thin aggregates, and then in the neon plasma, they're smaller aggregates, but they're still elongated. And you can see they're kind of spaced regularly, and that's because they're all repelling each other with their charge. So one of the questions we ask is like, why are they rotating? Well, those are those torques, and there's a variety of torques that you can get acting on the grains, which I don't think we're going to go into today, but that's another day. So let's talk about aggregates in space again. So we talked about if we want to build planets, we have to start with our dust. We have spherical monomers. They might be about 1 micron in size. And then we can start sticking the spherical dust together into aggregates. It may grow into about millimeters in size. And then about centimeter in size, you start considering pebbles. Well, okay, micron-sized dust sticks together very efficiently. Okay, you don't have to do anything and it's just going to stick. But it's really hard to get centimeter-sized pebbles to stick to each other. They don't do that. So at some point we hit something called the bouncing barrier, where now when you throw two things together, instead of them sticking together, they're going to bounce and they may fragment and they may fall apart. And it's like, how can you ever build a planet if now when you're trying to throw stuff at each other, it's just falling apart and destroying itself? So we get this bouncing barrier where we don't understand what's going on. And eventually you get to meteor-sized bodies, and then they have enough gravity to start collecting each other into rubble piles and eventually build planets. But there's this region right in here where we don't know the physics. And so one of the things that we can study is meteorites. So meteorites are very primitive rocks. They were formed 4.56 billion years ago, which is older than the age of the Earth. That's the age of the solar system. So these were formed at the beginning of our solar system when we had a protoplanetary disk. And you can see that these rocks consist of all of these little millimeter-sized bodies that are stuck together. They're called chondrules. So the question is, well, how do we stick these if you've played with little BB-sized millimeter things, they don't stick together. How do you get them to stick together and form rocks like this? And something that's even more curious is there's a group of chondritic meteorites, chondritic because they have chondrules in them, where all of the chondrules have these rims around them that are fine-grained. So it's like these millimeter-sized bodies picked up dust rims of micron-sized material, and they can use 3D tomography scans and actually get the 3D tomography of these chondrites, or they can cut very thin sections and use X-ray tomography to figure out what the grain fabric is around these things. So one of the questions we wanted to ask is, how do you build these fine-grained dust rims, and what do they look like, and what would they look like then when you stick them in a chondrite? So we have a couple of different collision outcomes. You can have just hit and stick where everything falls and it's nice and gentle and it just stays where it lands. Of course, if you have charging conditions, you can have particles that come in and they miss. And then if you have this intermediate speed, you can have stuff that comes in and hits, and then you have restructuring as it starts rolling and crumpling the dust pile. So Choo-Choo's done a lot of modeling like this and looked at the difference in the rims that you get under different conditions. And so this is particle accretion, where we're just adding one single particle at a time. And this is cluster accretion, where the dust is already in aggregates. And then the aggregates are landing on the surface. And you can see you get very different porosities. And the porosity is then going to change so if you have these chondrules that are dressed with this dust cloud, and then they dust rim and then they collide with each other, if it's a very nice fluffy dust rim, it could actually help them stick together. And so that porosity is going to change how they hit and collide and stick. So that's one of the things we'd like to answer is, if you have these different porosity dust rims and you throw two dust particles, two chondrules at each other, what is the collision outcome? And then if you have charged dust, you get very different porosities. Oh, Ansong, sorry.
So before you move to this, so when you consider big one and small one, the small size will also affect this.
Yeah, so you notice on the other slide, and you can see it here, that you get a lot of small stuff right at the surface. The small particles that can actually sift down through the dust pile. But when you have charged dust, all the small particles get repelled. And so then you have very porous rims that only have the largest monomers. And this is a 2D cross-section. So this would be something like we saw before, but now if you just take a single slice, you can see there's lots of voids in there. And so depending on the turbulence of the gas, because you need the turbulence to stir it up and give the relative velocities between the grains, and the amount of plasma in the gas, you can get very different types of rims with different porosities. And so that's kind of what we're investigating, is where in the disk, what kind of turbulence in the disk, what kind of charges do you have in the disk, and what kind of rims are you going to get? Okay, moving on to another place, lunar swirls. So the moon has a number of features like this, where you have these dark and light albedo patterns. And here's a zoomed out image of that. But this shows kind of the magnetic anomalies on the moon. And it seems that these albedo patterns, the light and dark swirls, are related to magnetic anomalies. So the theory is here that, you know, we get that dust that's lofted, and then its motion in the magnetic fields will cause it to preferentially move in certain directions. And so you can get the old material that's weathered and dark versus the new material that's light. So this is what I told you before, is that you can get a potential difference on the day side and the night side of the moon. So the moon is exposed to the solar wind, as well as UV radiation and X-ray radiation from the sun. So on the daylight side of the moon, you get plasma ions coming from the solar wind, and you get UV and X-rays that are going to knock off electrons. And so on the day side of the moon, you're mostly going to get positive charges. And then the photoelectrons that get emitted, they get recollected, but there's more that are being emitted than are being recollected at any given time. But then on the back side of the moon, the plasma, the solar wind does go all the way around. And so on the back side of the moon, it's just charging in the plasma with the primary currents, and so it becomes negatively charged. And so right here at the terminator, you're going from this negative charge to the positive charge. And people have estimated what are these potentials, and they've gotten potential differences that go as large as like 100 volts difference. And so then they're looking at, oh, how do you charge up the dust and figure out where it's moving? So this is kind of a picture of what the lunar dust looks like. You can see it's very irregular and kind of sharp and jagged, kind of like flint knives. So just figuring out what it's doing is difficult, but we can always go back to spheres for our first case and looking at the charging. So one of the theories about the charging is that when the particles charge, if they're charged by photoelectrons, the electrons are only going to be emitted by the surfaces that are lit. And so they're going to emit electrons, but now the electrons get emitted in all random directions, and they can actually collect on the surfaces that are not lit. And so if you look at how the charge is arranged, you can see that you can get pockets where you have a large positive charge right next to a very large negative charge. And so you can generate very large electric fields in these very small regions. And these electric fields can then be large enough to overcome the adhesive contact forces between the grains and actually knock them off. And they've done some experiments in the lab where they actually take a dust pile and they shine UV light on it, and they actually see the dust moving and spreading. The whole dust pile will just spread, and you can actually see the dust grains jumping. Okay, so some examples that are done in our lab, we've looked at building some dust piles. And basically, this is done in one of our plasma cells with the glass funnel. So we're just dropping in the dust grains, and then looking at how these piles accumulate and comparing to numerical models. And then what we can do is use a laser that's horizontal like this, and we can actually scan it up and down past the dust pile and come up with the 3D, rebuild a 3D model of the dust pile. We can also take a vertically scanned and get the whole 3D model. So this is an example, though, of what it looks like when you drop the dust. You can see all the trajectories. They're just bouncing all over the place. And then this is an example of a picture of that dust pile that you're left with after everything has come to rest. And so what we'd like to be able to do is to figure out then, okay, so now if we do have charging, how is that related to the porosity of the dust pile? And you can see just taking these interactions, you can get collisions, and these are just dropping under gravity. This is dust dropping under gravity from like all of, 6 inches max. And you can see how violent these collisions are as they land on the surface. So where is dust important and where is dusty charge important? Well, it's important everywhere in space, and we can talk about, how do you build planets, where it is in comet tails, the polarization of light, which can tell us information about magnetic fields. But the interesting thing is, we see them in dust in Earth too. So when they do silicon manufacturing, silicon chip manufacturing, you're etching these computer chips, you're using plasma, and you're etching away the chips, so you're creating dust. And so one of the things that they're worried about is controlling the dust so it doesn't ruin the chips. In ITER and other fusion tokamak devices, where they're trying to reach the conditions in the center of the sun, very hot plasma. The plasma actually eats away at the walls, because it's hard to build a chamber that can hold something that's the center of the sun. So you get this charged dust then that's in your plasma, and they want to know how is the dust going to be transported and how do we collect it and get rid of it, because then it's radioactive dust. It's not so very good. And even in the LHC, they have a problem with dust. So they're using these big, magnetic rings to confine their proton beams, and they have these UFO events, unidentified falling objects, which is dust for some reason that falls through the beam, and it's charged, and it messes up their beam. So we see it in all sorts of experiments. So, even with a couple of electrons on your dust, you're going to see the dust doing funny things. But that's it. And if you have other questions, I'm happy to answer them. And I will take them now. Actually, I can answer them later, or I can answer questions now. It is 4:45, so.
Very good. So now we have time. In fact, we have time for chat.
Okay.
Questions.
All right,
Come on.
start over here.
And so we have this.
So, talking about the growth barrier in your, is kind of like we don't know how planets are getting from this aggregate to pebbles to then the planetoids, right?
Mm-hmm.
So, when you were talking about like the filaments, the dust filaments, is like the theory that those dust filaments are acting as like a glue for those like pebbles, or?
Yeah, that's a possibility. So, so then when you have actually there's a lab where they actually shoot snowballs at each other to see how the snowballs will actually stick. It's really kind of a great experiment. They actually built a bow and arrow, so they can calibrate how their velocity of their snowballs, and they do it in the freezer. So their bow and arrow goes through the side of the freezer. There's a hole there, and they throw snowballs at each other. So so you can get them to stick together, and do they actually grow versus snowballs falling apart? But that is one of the thoughts, is that you could have frost rims. So this could be water ice that's instead of the silicate or metallic grains that are then forming the rims on the dust to stick it together.
Go ahead.
You mentioned how like on the moon, there are sometimes changes in the behavior due to like external magnetic fields. Have you been able to, or have you started modeling that in like a lab?
So actually, we did some experiments in the lab, and those slides didn't make it in here, where they actually recreated kind of magnetic anomalies like the Reiner gamma formation that I showed you, where they put in little button magnets and then dropped the dust in with the charged environment, and then when you turn off the field, they had a glass plate over the magnet so they could collect the dust, and the pattern on the glass plate looked remarkably like the patterns on the moon. So we do know that the magnetic fields and how they're oriented definitely change the trajectories of the dust and their motion. Diana, and then Suvadi.
At the beginning of the presentation, you said that when you have a plasma of ions and electrons, and there is dust grains inside that, the dust grains get charged negatively. Why?
Okay, so you have electrons and ions. Let's say that you have a hydrogen plasma. The ions are 1,837 times more massive than the electrons, right? So the electrons are moving a lot faster. So when you have your neutral dust grain sitting here, the electrons are faster, and so you're going to have a greater flux of electrons to the surface than you will ions. Okay? So that's always going to be true, that you have the electrons are moving faster than the ions. So eventually, though, now that you've collected a little bit of negative charge on your dust, the ions will be attracted. So now it's going to have more ions, and some of the electrons will be repelled. And so gradually the ion flux will increase as they become more and more attracted to the negative dust, and gradually more and more electrons will be repelled as you charge up, until eventually the number of electrons and the number of ions hitting per unit time is equal. And that's when you hit your equilibrium charge.
Thank you for the beautiful talk. Two of my questions I already answered. Another thing is that is there any correlation with the if the aggregation will be a cluster type or a particle type with the daytime which side it is happening, in the day side or in the night side?
Okay, so you're talking about the particle aggregation in the rims versus the cluster aggregation in the rims?
Yeah, which one is is there any correlation that one of them will be facilitated for the screening that is happening due to the photoelectrons?
With the electrons? How is it correlated with the...
Photoelectrons.
Oh, with the photoelectrons. Oh, yes, yeah. So you're right. You can have multiple charging conditions that are occurring. And so basically, you're always weighing your plasma density versus the energy of the photons that may be in the system. When we're in the lab, for sure, it's going to be mostly primary charging, primary currents doing the charging. When you're in space, yes, you're going to have photoelectrons. If you're in the solar wind is pretty tenuous, and so then the photoelectric charging is going to be more important than, say, probably the primary currents from the plasma in a solar wind. When you're in a protoplanetary disk, you still have a lot of gas left in the disk. And so that gas can become ionized by a variety of methods. It can become ionized just because it's hot. So we use something called the Saha equation to determine what fraction of the population is ionized based on the temperature. It can become ionized because of the gamma rays and high energy UV photons coming from either the host star or from other stars. It can also become ionized because you have radioactive decay of the other material in the disk. So there's lots of different processes that can go on that can create the plasma. So it depends on what period of time you're modeling for the disk formation and the disk evolution as to what is going on in the disk. And it's a very hard question to pin down.
Thank you.
Oh, Benny.
Thank you. How do you take into account the different waves in plasma?
The different waves.
Yes.
Oh, I am not taking into account I'm not taking into account waves here, but actually we do have the experiment that's on the International Space Station, and that one is in a DC plasma, so it's this very long, narrow tube. And when they do the models of just the electrons and ions, just the plasma itself, they do get ionization waves. And so in an ionization wave, you get a huge increase in the number density of the electrons, followed by a huge increase in the number density of the ions. But since they're not exactly correlated in time, you actually get a difference in the densities, and that leads to a big spike in the electric field. And so actually that has a lot of interesting consequences for the charging of the dust, because then the ion flow to the dust is not steady. So the dust will charge differently when the ions are flowing past the dust versus it's just a nice homogeneous plasma. So in that case, yeah, the waves make a big difference. Auntie Joe.
How accurate is your model?
How accurate? You know it's 100% accurate. It has no errors whatsoever. Yeah, so one of the things that we do have to do is assess the accuracy. And so you always go back to the theory. So are you able to recreate the OML charging if you have a spherical homogeneous plasma with equal temperatures? And so you go back to things like that. And then also for experiment, we can experimentally measure the charge. It's difficult, experimentally measure the charge on the dust grain, and then we can go back and compare our model to the model. What charge do we get on the dust grain, and is that consistent with the charge needed to float it against gravity? So does the electric field causing the ion flow, driving the charging current, cause the charge to be consistent with the charge we measure in the lab and consistent with QE equals mg? So we do have checks built in like that. Ben.
Yes, thank you for your talk. Actually, I have two questions. One is that in this kind of study of the dynamics of the aggregation, and can we use the tool like n-body simulation to study it? Because if it's few of dust, few of plasmas in the space, and can we use such kind of tool to study it? This is the first
Right,
question.
yeah. So I do a lot of in-body simulations. The samples I showed here were, just two bodies interacting at a time. But especially when we're doing, say, looking at the dust interacting with the flowing plasma, that's a big n-body simulation where we have, hundreds of thousands of ions and thousands of dust grains and looking at how they're all moving together.
This is a quite usual method that people are using to study the structure formation. Another question is that what scale of such kind of dust you have to take into account of gravity? Because in your, you just show us, basically you just use the electromagnetic
Right.
force.
So in a lot of the astrophysical environments, like if you're doing protoplanetary formation, everything's orbiting the planet, so the gravity just is setting this rotational frame. And so you're not really having to worry about the force of gravity in that case. Actually, the electromagnetic forces will be like 100 times bigger than the gravitational forces in that case. In the lab, when we're doing experiments on Earth, we're having to levitate stuff against gravity. And so in that case, gravity is one of the dominant forces. And so to the zeroth order, kind of the first order, QE, the charge on the dust grain multiplied by the electric field in the very edge, the sheath of the plasma, has to be equal to the force of gravity. And then we have some other interesting effects that happen. So the experiments on the International Space Station are in microgravity so that you can get around with having the gravitational force of being the dominant force that's acting on your system.
And also, for example, my question is the size of the dust. When it grows, then you have to, in certain period of time, you have to take into account of the gravity.
Oh, right, yeah. So, okay, so for when it gets to pebble size, then the dynamics are going to be more influenced by the gravity of the star than it will be between interparticle forces. So basically it depends on the charge to mass ratio. And the charge to mass ratio, though, can be as small as 0.03, whatever SI units go along with charge to mass. And you will see significant effects on the dynamics of the dust. Auntie Joe.
Do we have anyone else?
Yeah, Auntie had.
How do you know that the dust is always originally neutral?
We don't. But it reaches the equilibrium charge very quickly. So like in the lab, actually because when you're dropping the dust in, just shaking the dust around, you get triboelectric charging. And the dust can actually clump together. It's actually charged and clumped together. So we actually have to work very hard to break it up and drop it in through a mesh to break it apart. But usually we're not worried about that part of the curve where we're going from 0 to the equilibrium part of the curve, because that occurs very fast on the order of several microseconds.